Okay. Thank you very much. Okay, so at first I have to say good afternoon, everybody. My name is Masayasu Mimura, and before starting my lectures, let me say a few words on my background. And I came here from Meiji University, which is located in Tokyo. But so our institute is a little far from the main campus, about 30 minutes by trams, and the name is Meiji Institute for the Advanced Study of Mathematical Sciences. And this is URL, homepage of our institute. And so if you are interested in our institute, please visit to this homepage. And basically our institute has three branches, three divisions, and one is fundamental mathematics, it's really pure mathematics. And I belong to the second one, it's so-called mathematical modeling and analysis, like application-oriented mathematics. And now we have 18 professors, including associate professors and full professors. And now we have 12 postdocs. And then third one is mathematical education. And because in universities, many students who really want to be teachers in high school or junior high school. And also we have a sort of graduate school of advanced mathematical sciences, and we have a MIMS PhD program, and every year, of course, this is different from the PhD program in the Department of Mathematics. Okay, this is just our institute, and we selected 5 students for a year. And benefit for the student is no tuition fees and also like a salary, and for 20,000 Japanese yen for a month. So I hope they can survive, even in Tokyo. And I told you how the students are coming from the foreign countries. So our common language is English. Okay. This is sort of a short introduction of my institute. If you are interested in our institute, please come. I really want to welcome all of you. Okay, so let's start my lecture. Oh, sorry. Wait a second. What this?
Yeah.
Yeah.
The number of professors
yes.
is just for the modeling part.
Yes, right.
So there's also other people.
Yes, this is sort of algebra and geometry and also pure analysis. But honestly speaking, this is branch only the one. Okay, so let's start my lectures, and the title of my lectures: Application of reaction-diffusion system to biological and chemical systems. Mainly, I'm interested in emphasize about application compared with analysis. Okay, this is sort of the content or plan. Today, so I just introduce why I'm interested in the reaction-diffusion systems. And tomorrow, oh, sorry, now slightly changed due to the Professor Kim. Okay. Okay, so the second and third topics is a sort of the self-organization applied in bacteria colonies. And this is motivation. The research is a sort of motivation to understand the pattern formation in bacteria system. And then the fourth lecture is interaction of travel sport, but this study is coming from the combustion under the microgravity in space shuttle. Okay? But mathematically speaking, this is sort of the interaction of traveling spot in reaction-diffusion system. Okay, and the final one is a sort of ecological system, so-called competitive exclusion and competitor-mediated coexistence. I will, of course, in the Thursday, I will explain more precisely. Okay, but this is a kind of content of my talk. And let me start the first, the part, initiation to reaction-diffusion system. And the first thing what I have to tell you is what are reaction-diffusion system. And now in this lecture I will restricted the following more simplest the equation. So this is a Laplacian. This D is a constant matrix with a diagonal matrix. Okay. So this is an extremely simple case. And the F is given by the reaction term here, F1 and F2, Fn. That's the Y. Only the interaction among U1 to Un is given by only this one. Okay? This is an extremely simple case. Of course, if you are interested in the more difficult case, say this is non-diagonal or D depend on the U. Of course, you can study this problem. But in my lecture, I would like to simplify the situation that is easier for us. And the most simple case is this one. Okay, in the absence of the action. So this is just heat equation. And everybody knows the following. Suppose we consider the following initial boundary condition. And this is the zero flux boundary condition with the initial condition. So this is very simple. Then everybody knows that you tend to a spatial average of the initial functions. Okay? That means the diffusion enhances spatial homogeneity. This is common sense in our life. Okay? Everybody knows. Even my wife knows that this. So if diffusion interacts with the action, or if diffusion is coupled with the action, then we have the following reaction and diffusion system. Okay, and it is the same boundary condition. Okay, maybe here. Okay, and so this is the reaction term. This is a standard scalar reaction diffusion equation, not systems. And one of the typical example is the following KPP Fisher equation, which arises in the genetics problem. Okay, and this is just bilinear nonlinearity, 1 minus u times u. This is also growth term, and this is a sort of growth rate. Okay, and we also assume the same, the boundary conditions with the initial condition here. We assume that u not x is non-positive. So how is the behavior of a solution? Okay, so this is just nonlinearity like this. So if you are interested in the only the ODs in the absence of diffusion, so you can say, oh, this is a stable critical point and this is unstable critical point. And if we assume the initial condition, initial values u naught is positive, then every solution u tend to this one in OD sense. Okay. Now how about reaction diffusion system? We have the same result. say by using comparison theorem, and also the property of the heat equation. But probably if you're interested, prove this one. Okay, and then this result is extended the following by Cass and Holland, quite old classical result. When f of u is either convex or concave, then non-constant equilibrium solutions are unstable, even if they exist. Okay, so it means the candidate of stable equilibrium solution should be spatially constant. Okay, it given by the ODE information. Okay. Okay. So how about concave or non-concave or yes, non-convex case? The typical one is here, like this. This is a cubic nonlinearity, like this here. This is so-called Allen-Kahn equations arising in the two-phase problem. And same boundary condition, and the nonlinearity is like this. So in ODE sense, we have two stable critical point, and this is unstable. That's why. So we can say this nonlinearity is a bi-stable nonlinearity. Okay. As that, for this system, we already know the following. When omega is convex, in the previous result, independent of the shape of omega, but here we have to think about the shape of domain. Okay. If the omega is convex, then non-constant equilibrium solutions are unstable, even if they exist. So that is, the solution of this problem tend to either 0 or in 1 genetically. Okay. Of course, we have this solution. Okay. So this is also this very classical result. But this is result. This the theory is very give a very important information. If we change the domain omega from convex to non-convex, so what happened? In convex case, we have very beautiful result, and this result very similar result to given by ODE. Okay.
So here.
Yeah.
0 or 1, right?
Yes.
Not this kind of volume.
But this is unstable. You are not student. Okay. Okay. So how is the case of non-convex and non-concave? Okay. So what happened? And same problem. But omega is not convex. Okay. So what happened? And then done by Matano, and he proved the following: when omega is a suitable dumbbell shape, dumbbell shape is this is a bit more complicated, but dumbbell shape is like this. You can see, okay. So this is omega, okay. And if we consider the domain omega given by such a dumbbell shape domain, so what happened? Then Matano proved that depend on the f of u, there are a stable non-constant equilibrium solution, stable. And roughly speaking, here is almost 0, here is almost 1. Okay, so like this. And this is very narrow. Okay, so maybe you can imagine. Okay, by using the upper lower solution technique. Okay, and in this case is say u1. This is also u1, and maybe this is u2, something like that. Okay. So for the non-convex domain case, we have to think about the shape of the domain. Okay. Okay, so this is sort of a tentative conclusive remark. If we assume the omega is convex for simple case, then the asymptotic behavior of bounded solutions of a scalar reaction-diffusion system, so that of this problem, can be known by the information of the corresponding ODEs like this, or kinetic equation. Because in this case, generically, even if non-constant equivalent solution exists, they are unstable. Okay. Okay. So it means this is not so surprising because we know that diffusion enhances spatial homogeneity. So due to this result, probably someone asked me, why are you interested in the reaction-diffusion equation? Because the reaction-diffusion is so simple. Just you may study the ODE. So that is a true story when I was a PhD student, so like you. Okay? Okay, so here. Okay, so then how is the case of system equation? Okay, so I told you, so U is U1, U2, UN, okay? So how is N is greater than or equal to? What happened? Of course, we assume the omega is convex, okay? So non-convex is this is a slightly different story. So we have the convex like this. Okay. And then for this problem, I have to mention the great mathematician. Okay, here. So his name. Okay. Anyways, what happened? Okay, sorry. So at first we have to say sorry. So for this problem, the first obvious result was done by Conway, Hoff, and Smoller. And they say the following. Suppose the solution U is uniformly bounded in time. Then if D is very large, then U becomes spatially homogeneous after large time. And precisely speaking, at first you have to show the uniform boundedness of the solution independently of the diffusion. Okay. At first we have to prove it. Okay. Then after that we can say the following. If D is very large, then U becomes spatially homogeneous. And before proving this result, at first we have to study sort of the invariant set of solutions in reaction-diffusion system, but just I skip it. But roughly speaking, if D is very large, very, very large, so we may expect this result because diffusion enhances the spatial homogeneity. So like this. So this is mathematically we have to prove it, but intuitively these results are a little bit obvious, trivial result. Okay. Okay. And then when D is not necessarily very large, so what happened? This is a question. Okay. And then I told you before, so there is one great mathematician, Alan Turing. Maybe you may know his name, Turing machine in computer sciences. And he said the following: diffusion enhances spatial inhomogeneity. It's a sort of paradox of diffusion. Even n is equal or greater than 2. N equal 1, I already tell you told you, okay? But if n is greater than 2 or equal to 2, he said the following, so the paradox of diffusion in 1952. And after 2 years, he was killed by himself. Okay? Very sad story. So if you are interested, I will explain more precise story about him because I love him very much. Okay, so it means the following. This implies that ODE information does not necessarily give an essential information on understanding of reaction diffusion system with this one, okay? Okay? And he showed a very simple example. Oh, okay, sorry, this is just his paper. The title of his paper is not mathematical, phrase. Just, so the chemical basis of morphogenesis. Morphogenesis is a very important, the issue in developmental biology. And he said the following, mathematically speaking, if we consider a system, okay, and although it may originally be quite homogeneous, it means stable, spatially homogeneous equilibrium solution is stable in ODE sense. So they may later develop a pattern or structure due to the instability of the homogeneous equilibrium solution. This is sort of the destabilization of spatially homogeneous equilibrium solution, which is triggered by random disturbance. Okay, this the sentence says the following: diffusion may destabilize spatially constant equilibrium solutions of some type of reaction diffusion system. Okay, it's so-called diffusion-induced instability. This is very important. The keyword in my the lectures. Don't forget it. Diffusion-induced instability. What does it mean? It means the following. Okay, this is very simple. Undergraduate student. Okay, suppose we think about such a ODE, linear ODE. Then we know that 1 is a trivial. 1 is a critical point, and then you may easily prove, this 1 is asymptotically stable. Okay, can you do that? Okay, so this is the first step. Okay, so in ODE, this is 1 is a stable, asymptotically stable. Okay, then we think about reaction diffusion system. Of course, linear reaction diffusion system. So like this, we put here with Neumann boundary condition. In 1D case, okay, very simple case, interval from 0 to 1. Then we know that the critical point 1 is also equilibrium solution of this one because of the zero flux boundary condition. Then you can prove for some parameter regime of du dv, some parameters of du dv, 1 becomes unstable in reaction diffusion sense. Okay, this is very important. Okay, so if you think of ODE, this is stable. But if you think about such a critical point in reaction diffusion sense, depending on the parameters of du and dv, we may have an unstable. Okay, so this is so-called diffusion-induced instability proposed by Alan Turing. Okay, by using this very simple equation, because sorry. So, sorry, I forgot. This, the paper was not published in the mathematical journal. Okay, that's why he tried to write simply his result to non-expert. Okay, in mathematics. Okay. Okay. Yeah. Okay. Yes. And then this, the idea can be extended to the following. Diffusion. Okay. At first, sorry. Maybe you know, this is a kind of bifurcation phenomena. Okay. So mathematically speaking, this means sort of the bifurcation phenomena when the parameter either du or dv valid. Okay. Then in the stability change. Okay. From the stable to the unstable. This is sort of bifurcation phenomena. Okay. So, and then it means the following. So diffusion induced instability with a bifurcation phenomena generate pattern in the reaction-diffusion system. Of course, in the previous example, that's linear. That's why we don't have any pattern. But if you consider a non-linear problem, and the linearized equation has the previous assumptions, then we may have the following and the pattern. At first here, and put a small fluctuation here. Then, because of the destabilization and mechanism, we may have this kind of pattern. This is black with a white spot pattern, and this is sort of a stripe pattern or Laveron's pattern. And Turing said a small fluctuation, small fluctuation given to the reaction to the spatially constant equilibrium solution of the reaction system generated ordered patterns like this. So this is due to the diffusion-induced instability. And nowadays, we call such a pattern Turing patterns. But the serious problem is coming. This is 1952. At that time, everybody didn't believe his idea. Of course, mathematically, his idea is really correct. Just you check the eigenvalues. That's all. But the question is, are there any Turing pattern in our life or in the biological systems? Okay, this is a serious problem. Then after 2 years, he was killed by himself. Okay, so he had no chance to against for such the claims. But serious problem is okay. So I showed here. So if some parameters, say du or dv, are slightly changed in the system, so Turing said, okay, so we have this kind of pattern, this kind of pattern, this kind of pattern. And the mechanism is the same. Only the difference is the magnitude of the diffusivities. Okay, that's all. Mechanism is the same. That is very important information from mathematics, okay, or modeling and mathematics. Okay, but in 1952, so nobody believed such a very crazy idea. But the interpret is following. So this is a catfish in Amazon River, and this is like this. This is like this, okay. And so one of the Japanese guys, Shigeru Kondo, he's a fan of the Turing's pattern, okay. And he's a medical doctor, and he tried to look for this pattern. Okay? And finally, he found it. Okay. And this is sort of the support as example for the Turing, diffusion instability. But nowadays, not so. Nowadays, not. This is 1995 on the cover of Nature. So Turing patterns come to life. So gradually, Turing's idea, the mathematician Turing's idea, coming to the biological, the communities. Okay. So this is 1995. Okay. Okay, and then let me repeat again Turing's message. If diffusion is suitably coupled with a reaction, then reaction-diffusion system with this property may generate spatial and or spatial temporal patterns which cannot be expected by the corresponding ODEs. Okay, this is just Turing's message, okay? Okay. 30 minutes? At
3 o'clock.
Okay, fine. Okay, now let me show you more concrete example, okay, in our life, okay, according, to Turing's idea. Okay, so this this is sort of like a fire in stove. Okay. This is sort of combustion of a liquid, or in this case gases, liquid or gases. I don't know. I cannot pronounce it. Maybe could you help me? It's methane or I don't know. So maybe you know.
Methane? I don't know.
Methane in Japanese. Okay. We say methane.
We say so.
Okay. This is so methane. Okay. But correctly speaking, methane or something like that. Okay. Okay. Now we are interested in the sort of combustion, okay? But I told you, so my real original motivation is not this one, but from combustion in smaller than combustion in microgravity. So if you're interested, I will give you some paper. Okay, so methane. Okay. Methane is given by the CH4. Okay, this is the oxygen. Okay, and then this is CO2, and this is this. H2O. Looks simple, but of course in this process it is very complex. If you think about more seriously, maybe over 100 processes there. But we are mathematicians, okay? So we easily, simplify. The chemical reaction. Okay, now if oxygen is given unlimitedly or without limitation, then the system looks so simple, so like this, okay? So this is reactant, methane, okay? And this is product, and the K of T is a reaction rate, okay? And the reaction rate is given by the Arrhenius rate, and where T is a Kelvin temperature. And this is Kelvin temperature, this is Celsius temperature. And the K of T is, roughly speaking, is bounded and monotone increasing in T. So what that means if T is increasing, so K of T is increasing. Okay. So this is very the simple nonlinearities of K of T. And if the reaction is isothermal is a reaction, proceeds independent of temperature. Okay, so isothermal. Then we may assume the K of T is given by constant K. So then the model is given by the following: Vt equal dV. This is heat conductivity. So this is sort of diffusivity of the materials. Okay. Minus kV. This is reaction part, okay? And if K is constant here, so it given minus kV. This is no supply. But if we have some supply here, one candidate is given by the following. So this is same, and this is a sort of supplying term. If V is greater than V, if V is less than V star, so this is positive. So it's just flow in, and if V is bigger than V star, this is flow out. Okay. So this is a simple equation. Why? Because this is only the equation for V, and the model is a scalar and linear reaction diffusion equation. It's very simple. Because K and H and V star is given. Okay. So how is the behavior. So behavior is very simple. So this is our equation, linear diffusion equation with a reaction, and the reaction is linear. And this is the flux function with initial conditions. Then, if we use this sort of transformation from V to W by using this meditation, then V is given written as the following by using W. So this is heat equation. And so this is exponential part, this is decay, this is bounded. That's why when t tends to infinity, so this is zero, becomes zero. So we have this one. So here. So the easy, the result is given by the concentration of V tend to some constant. This is constant balance between this part and this part. So the reaction is very simple, not so interesting. Just the simple calculus for the undergraduate student. But this is not our case. Our case is our process is exothermic. Exothermic is the following. So we have this the chemical process, and then during this reaction, they produce the heat. So temperature is increasing. Okay. If temperature is increasing, that influence on the reaction rate. If reaction rate is increasing, so process is very faster. So it's a sort of couple between the chemical reactant and also temperature. Okay. Then we have to think about a new model, because of our system is exothermic reaction. Okay. So this is our model. The model is here. So T is the temperature at time T and position X in omega. But now we still assume omega is convex. And V is a reactant concentration here. And this is exactly the same one in the previous model. But K is not constant, but it depends on T. Okay, and T is given by the following. This is heat conductivity part. This is a sort of reaction part. So if the V is consumed, then the temperature increasing. Okay, and this omega is a sort of conversion rate. If the sort of fuel, so it's then omega is very big. And this is sort of the decay order, okay, from the system. Okay, so like this. So this is a kind of a system equation. The model is non-linear due to this one, non-linear and a system of equation. But in this case, n equal 2. Okay, here. So now we have to consider this system. In the previous model, it's easy to prove the atomic behavior. The question is, what is the atomic behavior of this system? This is our question. Okay? And then after suitable transformation, we just write down the following by using this is small epsilon here. And this is some constant, and the K is given by the sort of the monotone like this. So this is, in this case, K of U. Okay, and U is the temperature. Okay, so here. Okay. And let me show some numerical simulation. Okay. What kind of pattern appear from this system? And at first we have to assume the following. So here, A is here, and C is where? C is here, S equal here, H here, and we start here, okay, like this. If we specify the parameters in this setting, so we can have the following, the nuclides of F and G. F is so like this, like a cubic. This is F, okay? And G is monotone decreasing like this, okay? Then it is easy to say this intersection point P is a spatial constant equilibrium solution. Of course, I forgot to tell you, but we assume the zero flux boundary condition. Okay. Sorry. So this is a spatial constant equilibrium solution, and in the combustion, we can say this is a low temperature steady combustion. Okay, because quite low temperature, because we have a sort of balance between this. This always, gives the fuel. Okay, it's a bit quite low, but still, combustion persists. Okay, and then if we consider about the ODE case, okay, without diffusion, so this is very simple ODE. So by using the phase plane analysis, you can draw the trajectory or vector field. Then you can understand the assumed behavior of ODE. So like this. So ODE is the following. When epsilon is quite small, 0.001. Okay. So this is a clear point in ODE. Then if the initial value is very close to here, so this is immediately go back to this one. But if this is a little bit far from here, little bit here, then this is moving here and going back here. So if you precisely, check the vector field, you can say that this P is globally stable, assumed stable. Okay. Here. So it means the following. Okay. So in ODE sense, the result is not so interesting because there's no, limit cycle. Okay. Also no chaotic behavior. So very simple. Every solution tends to P. Okay. Now, coming back to the reaction-diffusion system. Okay. So reaction-diffusion system here we put here, and the zero flux boundary condition with some boundary initial condition. And at first we can say the following: if P is locally assumed stable, you can prove in a mathematical way. Okay, this is locally proved in the assumed behavior. So it means if we have a 3-point disturbance in P, if this disturbance is very small, then immediately this disturbance fade out. So we have this one. So not so interesting. Okay. And so how about the disturbance are not so small? So let me show some numerical example here. This is but this is not so small. Okay. And D is 2.0 and epsilon is like this. So what happened? Not so interesting. So here, why I said not so interesting? So this is a sort of the stimulus, or in combustion way we can say initial ignition. Okay. So this is sort of and this is sort of the combustion zone here, and that's combustion zone is expanding here. And then this is a sort of annihilation occurs between the two rings. And also this is also annihilation with walls, boundaries. And finally, we have the following: nothing particular occurs. Okay. But this is, I told, this is very similar to the forest fire. Can you imagine forest fire is burning like this? Okay, but inside is almost burned out. So never ever coming back. So if you have two, it's like this, okay? And this is annihilate, okay? That's all. So this is very simple example, a simple example of fire, forest fire. Okay. So nothing interesting from pattern formation viewpoint, okay? Okay. So, okay. What is this? Okay. Anyway, so. Okay, and then this is just a typical, the snapshot, okay? Look at here, this is just expanding, okay? Such an expanding ring reminds us the one-dimensional traveling pulse solution. Maybe so I don't explain what the meaning of traveling wave. Probably, maybe you know. That the traveling, the pulse solution is so that traveling wave solution is like this: z equal to x minus ct, but c is unknown because at this moment, and the z is just a whole interval. Okay. Then putting this functional form, putting here, then. So this is the ut, this is the uxx in 1D case, okay? So we have the following equation with a boundary condition. Boundary condition is a z equal plus minus infinity, uv becomes p. Okay, so the question is how to obtain the solution u with z and c, okay? So this is a kind of, mathematical question on the ODE situation, okay? But now I will show some numerical result following. This is a traveling pulse, so like this. So this is P plus minus infinity, this P. And this is U, this is temperature. This is V is reactant. So such a moving this way, it means this is okay. This is sort of low temperature combustion, okay, and this is sort of the burning zone, and the temperature is increasing. Instead, fuel or reactant, this is sort of the decreasing here, and this is moving this way with some velocity c. Okay, so maybe if you are interested, you should try to prove. The existence of traveling pulse solution. I have not yet proved it. Okay? And then interesting in the following. Okay? Suppose we have the following two initial traveling wave. This is moving this way, this is moving this way. Okay, so what happened? So just moving here. Okay, here. And then nothing happens. So it's a sort of the annihilation. So we already know this result by the previous annihilation of expanding rings. But mathematically speaking, it's not so easy to prove the annihilation of the expanding ring. The first step is to study the existence of traveling pulses in 1D case and annihilation property in 1D case. This is the first step to consider the mathematical problem on this problem. Okay? Okay. And I forgot to tell you. Oh, yes. Oh, this is a sort of different. This is a sort of the Korteweg-du-Bourrier equation. And probably maybe you know that in the KdV equation we have a sort of the family of solitary wave solutions like this. This is soliton. We call solitons. And this soliton has some parameter, a family of solution with a parameter c. If this same c, if amplitude large, so you see the large, so this large is very faster. And if you see the small, so small amplitude is slower. That's why we can see the falling. So this is a slow soliton, this is a fast solution. Then this is space, this is time. So this is very fast and slow, so it's a sort of, a collide. You can expect. And then we can sort of the crossover. Okay? This is probably nowadays very old, the mathematical result in nonlinear dispersive equation. Okay? And then this is a sort of the contrast between the two cases of the interaction of traveling pulse solution. This is a sort of the annihilation property, okay, in nonlinear dissipative equation. It's like a reaction-diffusion system, okay. And this is a sort of the particle-like interaction arising in nonlinear dispersive equation or solid KdV equation, okay. And for long time, yes, here we have believed annihilation property of traveling pulse was believed as an essential feature of the reaction-diffusion system, or roughly speaking, nonlinear dispersive equation has this kind of property. And the nonlinear dispersive equation has the following property, and the nonlinear dispersive equation has this kind of property. This is sort of the contrast or difference between the two very important equations. We believe this kind of difference for a long time. But this is not correct. We could find. Okay? Okay, so now, almost 10 minutes, we move to the slightly different situation. So D is 4.5. In the previous one, D equals 2.0. Only the double. And some parameter, other parameters same. And same initial condition. Okay, so what happened? So you can see a very complicated pattern appears. Only the difference is that the value of D. Only the D is just double from 2 to 4.5. That's all. But that the resulting dynamics is quite, the hard, the problem. Okay. And then so look at these dynamics carefully. At first, this here is the same. This is a sort of annihilation, okay, and this is annihilation. But the interval here, in the previous one, this is sort of the annihilation occurs, okay. But in this case, this is not annihilation, okay. This is moving this way. A kind of reflection occurs. And this is moving this way, this is moving this way, and this is moving. So this is splitting. Okay, here. And also you can see maybe look at here. There is some the rule there. What kind of rule? Rule is the following. Disappearance of spot in overcrowding areas. So if it's very, the spot is very, crowded, okay? It means very, the combustion is occur very actively. Then no fuel or no reactant, so that disappear. Okay? And if this crowding area, so then we continuously supply the fuel. That's why a spot will appear. So it depends on the area. So it's a very complicated pattern occurs. Okay, it's a very hard problem to understand. Okay, this is 3D. So like this, okay. So, as I told you, if you think about ODE case, so ODE case is very simple. Just every solution tends to P. That's it. But if we consider is a reaction-diffusion system, of course, depending on the parameters, we may have such a very complicated pattern. Okay? And probably nobody could expect such a pattern occurs. This is a kind of the attractive example for me to study the reaction-diffusion system. Okay? Okay, so yes, I repeat again. So all this dynamics is very simple because any solution tends to P. However, reaction-diffusion system generates so complex pattern because it depends on the parameters. Okay. Okay, and then we have still many mathematical problems. The first one is when D is 4.5. What is the reason why such complex pattern appear? Okay. The second, what is the mechanism behind the transition from type 1, so here, the 2.5, this is very simple, to type 2. It's sort of the transition process in pattern formation. And then, so this is a very nice mathematical problem. And then I'm sorry, if you are interested in the mathematical analysis of these phenomena, please, come to our papers. The first paper done by A and Nagayama, they are my former PhD student. And this is just 1D, pulse-pulse interaction. And we extend this result to the, higher dimensional case. So in this case, two dimensions, so that interact spot. So this is moving here to what happened. And I didn't say anything about, the interaction, but in this case, if this is moving here, okay, slowly, then never ever annihilate, the moving here and going back. So like a particle-like phenomena arise in the reaction-diffusion system in some situation. Okay, and this is this result proved by using center manifold theorem in infinite dimensional dynamic system. Okay, what is this? Okay. Maybe so I hope you to understand why I'm interested in the reaction-diffusion system. And the research of reaction-diffusion system essentially started in 1952. Okay, just Alan Turing proposed a Turing diffusion instability, induced instability. And then the target of reaction-diffusion system is to study the pattern and waves arising in reacting and diffusion system. Okay, and in order to do that, modeling is the first important job, and then analysis with simulation is needed. Okay, so probably it's for the part 2, 3, 4, 5, we mainly talk about modeling because analysis are very poor. Of course, I'm poor, but so up to this moment, mathematical the analysis is really poor in this field because this is really qualitative behavior. Okay, and when I was in the graduate student, the main target to the reaction-diffusion system is just global existence, okay, or assembly behavior, something like that, okay. But at that time is the result is so simple. But now is we are interested in the sort of the transient behavior, okay. Transient behavior very important. For instance, if that is a traveling wave, two traveling is moving like this, or it's just annihilation. This is really transient behavior, okay? Not asymptotic behavior. But this is our target, okay? Okay, so Sorry, this is my final, slide. So maybe I have to stop. Thank you very much.